Okay, this is Euclides Rodriguez. This is my presentation for homework number 4. It is the final project in the Data 622 Spring 2024 semester. The data set that I used for this homework was the a used cars data set that I found on Kaggle. It was given a good rating in terms of being a clean notebook and usability. And I thought it would be something that's practical that we could use as a presentation for this homework. All right, so just to start out, I guess we imported our data here and we just have our showing here our list of uh, features that we have for the data set. We have the make, model, the year, transmission, location, and some characteristics of the car itself. And the target variable is the price. And really, what we're going to try to do in this presentation is to try to predict the price of the car based on all of these variables that we have in the data set. So I start doing some data exploration just to understand what the data set has and uh, try to I guess the first part of it is to do the data preparation. And I think initially what I noticed when I opened this up was there was a lot of mixed uh, variables with mixed data that had both string and numerical values. Like for example, this engine variable here has 1198 cc for the first row. So I kind of went through the process of cleaning that up on my first go around. So that's what we're doing here in this first set of coding here is that we're splitting up the data and removing any of the string variables and separating out the data so that each numerical value has each numerical value within the data has its own column. So for example, we took the max torque and we took the RPM and then we also took the displacement, which is I'm assuming is this NM. And then we split that up into two columns so that we would still keep the data that was original to the original column, which was max torque and included RPM at nanometers. And similar to max power, where the max power was rated at a horsepower for a certain RPM, we split that up into two columns, removed all the strings, kept the horsepower, and kept the RPM. All right, so next time we're just looking at our data, seeing what we could do here. I'm taking a look here at all of our numerical values and just taking a look to see what the range of information that we have here. We have the max, the mins, the means, and the median shown here, and our counts. Um, the next item I wanted to tackle was the categorical features that we have here. Really, because I'm using Python as my base software for this homework. Both the um, TensorFlow and the XGBoost packages don't accept the data readily as categorical values. So I think the first pass I did here was try to identify what the categories were and then to try to split them up into one hot into using one hot encoding, which I do a little bit further down here. Um, One thing I did do was I kind of removed uh, from from our data set here. I dropped one of the columns, and that was let's see if I just show that. Where did I pick that up here? Um, I picked that up here. So I ended up dropping the model because there were just 1,000 models, and when I thought out when I was going to have to one hot encode each of the categorical values. This data frame would just be just way too large and just not useful for this project. And the same thing I did for locations. I could have kept the locations. It was 77, but I kind of just left that out because I thought that was too big of a threshold here. It would make our model too big. Moving forward, the next thing I did was just take a look at the missing values. I see there wasn't too many missing values, so I really didn't think it was necessary to have to impute any missing values to try to put like a median or a mean in that value. So I just kind of did it carte blanche. I just removed all the values. It really didn't affect it too much. It dropped our data set down to um, 18 1,872 observations, and I think our original data set was just like a little bit over 2,000. So it's not we didn't lose too much. So I thought that was like a reasonable approach, so as not to distort the original data set. Okay, and this is what I was speaking to a little bit earlier. Because of the Python packages that we're using, they're really formatted to, or they're really set up to take either these Boolean values. So, for example, like in this original column, the original column was owner, and it kind of identified whether it was one owner prior to it being sold, the second owner, there's two owners or three owners. So what I did in this, what we did with the one hot encoding is that we separated each of those categories into one variable so that we could do a 0 and 1 for each. Um, for each variable or each category within that original owner's variable. So we kind of go through that here, and then we see that our data set just becomes a lot wider. So we keep on moving forward. Okay, so the first model that I used was the XGB boost modeling. This was one of the models that I did not use in the semester, and based on our discussions in the classroom, um, this was one of the items that one of the machine learning tools that is most readily used in the industry. So I thought it was pretty important to use it for at least once in the one of the homeworks that I did for this semester. So we start out by splitting our data into our train and test set. Very similar to a lot of the other types of machine learning algorithms. The raw data, we really want to scale it so that it really doesn't affect the model. If you put in raw data and you have one variable that has a range from 0 to 10, and then the next variable has a range from like 0 to 2,000, that can really affect the performance of the model. So what I've learned throughout the semester, and I'm applying it here in this class, is that we have to scale our data set so that it has some consistent values to work with. So we go through creating the XGB boost model. And when we I guess create our model and we fit our data, we saw that we had an R squared of 8.82, and our mean squared error was actually pretty large of 814,000. So I guess I try to visualize how, I mean, it's nice to have these values here that are statistical metrics for how well your regression model is performing. But also, it's also nice to have a visualization here. So I think in this first model here, in this first plot here, I did a plot. On the x-axis we have the counts of all the data points, and then the price on the y-axis, and then I had it categorized by the actual value and the predicted value. And you can see for the most part, a lot of them are pretty close. And then there are a handful of actual and prediction values that are pretty far apart. And I think to, I guess, more clearly demonstrate that, I did the second plot here where on my x-axis I did the actual price, and then I compared it against the predicted price. And when the red line here, the diagonal line is the actual price, so that gives you what the value should be. And then what's nice about this plot is that it shows you, whether the predicted values were either higher or lower than the actual values. So overall, I mean, they probably could have done some additional hyperparameter tuning on the XGB Boost model, but I guess for this initial, I guess for it got the point of, we got a decent um, model at 80.82. Definitely room for improvement there. Okay, and then so the next model that I used was a neural network model, or using TensorFlow. Um, and similar um, to the XGP Boost model, I kind of used what was nice was I used the split data that I already previously used. So I used the X train and Y train and X test and Y test values that I already split from my XGB Boost model. And I kind of used that to import it into my neural network here. And quick little item that threw me off was, for whatever reason, like when you have to input your X and Y values for the neural networks, they have to match. And so that kind of threw me off for a bit here. So I had to change this Y train, um, uh, I guess, variable here. It was originally like an integer value, and I changed that to a float. So that enabled me to run this neural network algorithm here, which allowed me to process the model. We set up the model with pretty much 4 layers or 4 neurons. We use the ReLU activation function um, in order to produce the neural network model. And then we ran the model for 30 epochs. We definitely could have ran that a little bit higher, and I played around with it a little bit and saw that I got better results. But I guess for the purposes of this class, just to demonstrate the use of the neural network algorithm, I left it at 30 epochs so that it didn't take up too much processing power. And I go into my predictions, and um, definitely perform better than the XGB Boost model without having to do too much to it. I don't, I think definitely if I added additional layers or nuance to the model, and then I increased the number of epochs, I definitely could have gotten this number up way higher, probably into like the 0.9 range. So at face value, I think the neural network performed better. And then just to similar graph here, where I'm just showing the actual versus predicted values. I'm just giving a sense as to what the original values were, or the actual values in our y-test split was versus our predicted values. So overall, I guess in conclusion, I think both models um, uh, perform rather well, given that we didn't do too much data manipulations or hyperparameter tuning. That's something definitely we could have developed a little bit further, but given the base models that we did use, I mean, they were both quite effective. Definitely, the neural network seems that it would probably give us the easiest pathway to get a better model that predicts the values more accurately. I think definitely I would have gone with the neural network. It just seemed to uh, do it fairly well without having to do too much to it. So in conclusion, now it's my presentation for homework number 4, data 622 at CUNY School of Professional Studies. Okay, thank you very much.